Welcome back. We are starting a new chapter today. In this new chapter, we'll talk about electromagnetic waves. So, we have actually heard about this word electromagnetic waves from a very long time. We said that light is an electromagnetic wave, and all these things we have already heard about uh, this a long time. So, we were going to take slightly more rigorous and mm, good understanding from the basics of electromagnetic waves. Because now that we are very familiar with electricity and magnetism, it is possible to put together the so-called electromagnetic waves, okay, and see how it works. Now we'll start with a very simple thing that we already know of. Okay, let us say um, you have a coil, a solenoid, what we call. So this is the coil. Okay, like this, you have a coil, full coil up to here. Okay, and that coil has current going in this direction, going around that, coming out. So if you switch on the current for that coil, uh, you can see that we can create a magnet. We know that by doing a solenoid, we can create a magnet. So you can see that there is a I have not kept a magnet here. Okay, it is like a magnet. How a magnet can give magnetic lines, the force field or magnetic field what we have around that. So it was created by the electric current that is flowing through this. So I studied this work, and he showed very clearly how electric current, when passed through a conductor, can create a magnetic field. And we kind of make a very simple statement saying that electric current produces magnetic field. Fantastic. So no doubt in that we made a nice statement here. Now let us see what Faraday did. Okay. So here you can see Faraday's law of induction talks about whenever you move a magnet within a coil like this, okay, it kind of produces electric current. You see that? So when a magnetic field is moved here, okay, in the sense that what you are doing is that magnetic field linked with this coil is getting changed, no? Either through movement of the magnet or through maybe another coil can switch it on or switch it off or something like that. We can still make the magnetic field around it, around the magnet, go and touch uh, these wires, and they keep changing the magnetic field. When they change, it produces the current. There is no battery anywhere here. It just directly that produces the current. So now we can make a statement. The Faraday's law says that changing magnetic field produces electric field. Okay, it produces electric field, and that field basically, when connected, see, this is a voltmeter. It shows what is the electric field between, what is the EMF between these two. Okay, so it also produces a little bit when you close the circuit, it gives the current, but it produces the electric field. Or now you can see these two statements. One statement says that changing magnetic field produces electric field. The other statement says electric current produces magnetic field. Okay, they are quite similar, okay, and symmetrical, but not fully. Okay, in the sense that if I had said, for example, electric current produces magnetic field and magnetic current produces electric field, it would have been a very nice uh, symmetrical statement. Okay, I didn't say that, so there is a slight difference. And or we could have said, for example, that changing magnetic field produces electric field and changing electric field produces magnetic field. Even that could have been very nicely symmetrical. So scientists actually often worry about such things. You know, the world, they think that the universe has to be quite symmetrical about things. Yeah, they worry about it, and they worry about the beauty of things. So they think that it may be possible to show that that is true. So Maxwell, okay, James Maxwell actually took this effort. Okay, he said that he said changing magnetic field produces electric field. He wanted to change the second part and say instead of electric current, he would say changing electric field produces magnetic field. If I say so, then it will be very, very symmetrical. So he said that we will try that. We'll see whether it works. Okay. So now we are going to move to that part, trying to see how to make it very, very symmetrical and what is the difficulty in that. So then we will come back to electromagnetic waves. Okay. Now what we will do is we will move on to understand how to make this work. Okay. How to make this, how do we get this symmetry? We'll try that now. So let's look at the scenario and get back to our understanding of Ampere's law. Okay, like Gauss law in in electricity. Okay, where you have worked out electric field and charge and all. There is an Ampere's law in current electricity. Okay, there was which connects basically both magnetic field and electric field. If you remember right. Okay, if you remember, what does our Ampere's law say? Suppose if I take one point here around this is just a conductor through which current is flowing. I just magnified it and shown it as a big conductor. Current is flowing through that. Okay, now if I actually take one loop around this, which are equidistant everywhere. Okay, if you take for example, then we know that all these points in the on that circle, B is magnetic field that you produced is same, and we also know that magnetic field is basically in the direction of tangential direction like this. We know that this is how the B is. That this current is producing the B like that. So we also know that if you actually do this B at every whether you have at every point, if you basically take the B and multiply it with basic, the length of this loop and do an integration over the whole loop, that means if you say integral of B dot dl, okay, over the whole loop. So when you put this is basically called as a closed integral over the loop, path integral over the loop is equal to, okay, this will be equal to the current that is enclosed within this. Current that is enclosed within this, we'll call it as I, and with a one more constant called mu naught I. Okay, so like how we talked about in the Gauss law, integral of E dot dA is equal to over the surface is equal to charge enclosed within this divided by epsilon naught. So we had, this is our Gauss law and this is our Ampere's law. If you look at, there is a symmetry. There is a certain thing that you can understand is in the Gauss law we take a surface, okay, a closed surface. So over the closed surface we take flux, okay, that is E dot dA is nothing but field into area which gives out flux. Okay, that flux will be actually equal to Q by epsilon naught, the enclosed charge within that. Actually, you know what it is saying? In some sense, it is saying that this electric field is because of the fact that there is charge inside. Okay, so the electric field, if you see and compute all the flux, that must actually take you to the cause of that electric field, which is nothing but Q. So Q by epsilon naught. Epsilon naught is just a constant to get the units right and values right. Okay. Now, however, here also it is the same thing. What is causing the B? The electric current that is flowing through that is causing the B. So Ampere's law tells us that if you take the B, okay, on this line, which is now we are not taking a full closed surface, we are taking just a single loop, okay, which is actually having a surface here. So what we are doing is we are taking one surface, open surface. Okay, open surface, in a sense it is not a closed surface, it is just a surface. It's not like this. Okay, it's just a surface. And that surface has a contour, the end of the surface basically. contour, and on that contour we are looking at B. Okay, at every point you take B and you take the small length at that point, tangential one, and dot dl, that is, you multiply that. Dot we say because we have to take B along that direction. If the B is like this, then you have to take the component along the direction of that. So if you multiply that, I'm not going to very too much deep into the Ampere's law, which we have already done so. So please refer back to those videos. Here I'm just kind of uh, revisiting that because it is required here. So B dot dl, okay, that is basically if you integrate the B into length over the whole place, okay, so whole loop, you will get what caused it. Okay. What caused it is I, the I that is flowing through this. So the I that it contains, the loop, the surface, what you have, whatever the I that is crossing the surface. Okay, it is not the loop that contains the I, it is the surface that you are actually having. Okay. That surface, some I is passing through that surface. Now you take that I. So you will get that I into mu naught. So this is basically our Ampere's law. Okay. Now if you take, for example, I will erase the Gauss law. We are not going to use that. Okay. So instead of a surface very flat like this, you could take a curved surface too. Even then the Ampere's law actually works. Okay, you can take a surface something like this. Okay. And everywhere the B need not be same. It can be different also on those points. Okay. As long as you multiply it properly. So if you can take a surface like this, okay, this is like a surface, you can see that uh, it's like that net that you use. This is a called as actually butterfly net, which catch the butterfly. Okay, so it's basically like this. This is a net. Okay, so fundamentally it is a net like this. Though this is actually an ellipse like before. Okay, in the sense it's a circle like before, and you have here the surface is not a flat surface. It is a surface which is basically a net like surface like this. Okay, even there if you say, okay, the current that is passing through each of those points, if you take and basically whatever is cutting the surface, if you add all that up, that would basically be equal to, into mu naught will be equal to V dot dl on this. So surface, actually the shape of the surface does not matter. It need not be a flat surface. Could be any shape the surface is. Okay. So that is why wherever you take, and it may be a any shaped surface, it doesn't matter. Still it works. This whole Ampere's law works. Okay. Now even suppose if you take the surface, if you take the circle or this loop inside here, okay, here, take the loop inside, then the B you can calculate here by finding out B dot dl is equal to current that is enclosed only within this surface. So the total current will now be less. So hence B also will be less inside this. Okay, so everywhere, I mean whether you take it outside or inside, everywhere this Ampere's law works. So you can use it to calculate B. Now this Ampere's law, now we will take one step forward and show where it fails. Okay, we will show a place where Ampere law seems to fail, and this is what Maxwell did. So let us take a scenario, okay, where we have a circular plate here. Okay, you can see there is a circular plate here. One more circular plate here, separated by certain distance. Okay. So this is what we call a capacitor. We call it as a capacitor. So you know that you have studied the capacitor. So what we are doing is that to the capacitor we have connected wire here and another wire this side, and we are sending some current through this. Now what we are sending here is actually a AC current. So we are sending a AC current. So if you send a DC current, the current will actually be used initially to charge this up, and afterwards the current will become zero because it is completely charged. But if you send a DC current, then it will charge this and discharges, charges and discharges. How it happens, we have seen this, how a capacitor works in an alternate current. Okay, so in an AC current. However, it is a current. Okay, it's a function of time, that's all. So you are sending that current. Now the same current is coming this side also. So in such scenario, if we apply Ampere's law, what will happen? Let's see. So what we are going to do is we'll find some point here, somewhere here, and try to find out B at this point. Okay, let's say this is the point. I want to find out B at that point. So to do that, I will take one loop, including that B. That loop will go around the current, okay, which caused it. So now if I do B dot dl on that, okay, integration, that means it is B into dl at every small point and add all that up. The summation integration is nothing more than that. So you just add all that up. That must be equal to current that is flowing through this. So that's the current flowing through that is I. It will be like this. So this equation holds good. Okay, you will have, really speaking, you will have certain B here. So that B may not, B is not a constant B. Okay, B is varying because it is current is also varying. So B is varying, but it is there. And there is a B. We can write an equation for B as a function of time. Now, so far so good. Ampere's law worked. But remember, we said that Ampere's law should work whatever may be the case of the type of surface that we take here. Here we have taken this yellow surface which is very plain. Okay, now we will take some peculiar surface. Okay, so the surface, I'll just tell you the surface how it looks like. Let's take this surface. Okay, so I'm going to take a bowl kind of a surface. Look at this. I'm taking the same kind of a contour here. Contour is same. Okay, but the surface is not flat. The surface is like a bowl, and that bowl base we take it in such a way that actually goes around the plate here and passes through the center and comes out here. I can take that, isn't it? I can take such a surface. So when you take such a surface, also we should have our Ampere's law working. Now look at this Ampere's law. B dot D is equal to B dot, right? So we're going to try this Ampere's law on this. So we are still taking the same contour. Okay, on this contour, we calculate Ampere's law. So B dot dl we will do is equal to, okay, the current that is cutting across and going through the surface. So this surface is here. If you carefully watch, okay, there is no current flowing inside this. There is no current flowing inside a capacitor. There are no charges flowing, nothing. So the charge that crosses the boundary of this surface, the charge that cuts across the surface and goes around, goes that side, is zero. That means there is no current that is flowing. So if there is no current flowing, left side is same as B dot dl and right side will be zero. So it will be zero. Now you see here what is happening. Okay, carefully watch here. We have taken exactly same kind of a surface, as the same kind of a contour as like here. Okay, so if you take this contour here and take only this surface and not the bowls kind of a surface, if you take this surface, current passes through this and hence it will be equal to mu naught I. Okay, whereas in the other scenario, when you take it bowl kind of a surface, okay, curved surface like that, now there is no current passing through those surfaces. It is E. What you are showing here is electric field. It is not current. Hence, it is zero current flowing through that. So we are equating. We are just principally following the Ampere's law, but we are not getting two equations which are similar. So in one scenario it gives mu naught I, in another scenario, in one scenario it shows that B is 0. In another scenario it gives some value of B. So is magnetic field existing here, a non-zero magnetic field existing here, or not, depends on whether you have actually taken the internal surface directly straight here or around this. And this is not how Ampere's law works. Ampere's law should work consistently all the time. So that means that there is some problem here. I hope you appreciate this problem. Okay, the problem is Ampere's law says that if you take the surface here, you get certain value of B. If you get the surface there, it tells us that this value is 0. Okay, and the value of B will tend to become 0 here. So how can you have at the same point two different values for B? One being 0, other being a non-zero value. So if that is the case, then some flaw is there. What is that flaw? So that is what Maxwell worked on. So Maxwell said that this flaw can be resolved if you think it little differently, okay, slightly differently if you think. So what I will do is I will actually take, instead of a bowl like that where it is a little harder to compute, we will take actually some kind of a tiffin carrier kind of thing, tiffin box, okay, where it is flatter here. Okay, this part I want flat, so that it's a flat circular disk I want on that plot, so that I can do some computation very easily, though the computation works in either case. Okay, so I will take basically a surface which is like this, okay, where we can see that this path is same, this side we take here, and this is another disk here. Okay, this is a surface which is uh, parallel to these parallel plates. This point is actually parallel, a circular point, face parallel to the these plates. Okay, and then like a tiffin box, it comes here and ends here, and this is the open part of the top part of the tiffin box, like that. That is the contour. So if you take this, now you can see that, I mean, this is similar to that. It is just that I didn't want a curved base. That's all. Okay. So now what happens is you can see very clearly here, okay, that though the current is not actually flowing through this, okay, but there is something that is happening there. What is happening? There is electric field, and electric field is continuously changing. If electric field is not changing there, that means that there is no current flowing here. That would be a DC scenario. Okay, now we know that electric field is changing. So that is why you are having current here in the first place. So electric field is actually changing here. You can see. So and how do we now work with this electric field? What is the change that is happening? What is the electric field we are seeing? What is the amount of flux we are seeing here? So let us calculate that. Okay. So I will say the electric flux that is going from this side to this side. Okay. If I have, let us say, E is the electric field. There is constant electric field in the middle everywhere. So electric flux, I will say phi E. So we used to use phi for magnetic flux. So I don't want to use the same just phi. So we will use phi E, means electric flux. So electric flux inside will actually be equal to electric field, okay, dot A. Like phi is equal to, in magnetic field we used to say phi is equal to B dot A. Okay, I mean even electric flux also E dot A we used to say. Okay, so dot A, but however it is, since it is perpendicular to the surface, okay, the angle between the vector area vector and the surface and the E is 0. So cos 0 happens to be 1. So we simply can say EA. Okay, so cos 0 basically. Now, what is the value of E? value of E between two phases of a parallel plate capacitor, what is that? We have already kind of computed earlier, which is Q by epsilon naught. Q by, if Q is the charge on this, it will be Q by epsilon naught A. Okay. So into, this is our E, okay, into A. Cos 0 is 1 anyway. So this will give rise to Q naught divided by Q divided by epsilon naught. But understand one thing, this Q is not a constant Q. This is the Q that is varying here. It is a function of time. So it's a Q of t. So it is varying in time. Okay. Now what we will do is we will actually now say that we will find out how electric field is varying. Flux, how much is flux varying? So we will compute basically varying flux rate of variation, rate of change, flux rate of change. We'll calculate. That should be basically d phi e by dt. Flux rate of change is d phi e by dt. So if that it is d phi e by dt, so on the right side also we differentiate, which is nothing but d by dt of phi q of t by epsilon naught. Or we'll say 1 by epsilon naught, we'll take it as constant outside. Okay, and this is nothing but dq by dt. So we got change in flux, okay, change in electric flux, rate of change in electric flux is equal to 1 by epsilon naught into dq by dt. Or I would say, okay, let's put it here, dq by dt is equal to epsilon naught into d phi e by dt. So what we are going to do here is we will call this dq by dt as displacement current. Okay, so we will name it as, let dq by dt is equal to id, okay, which is called displacement current. Now if you see here, okay, is it an appropriate term? Okay. So if you watch carefully, we always use dq by dt for current, but when the charges are flowing, okay, how fast they are flowing, dq by dt, that is what we actually call it as current. That is our conduction current. That used to be basically our regular definition of current, dq by dt. So dimensionally, taking dq by dt as current is nothing wrong. Dimensionally it is current, but it is not really current. No charge is actually flowing here. What is happening is that the charge is varying at the surface. On the surface, charge is varying, and that is causing the electric field to change. So we will say that dq by dt is some kind of a current. We'll name it as displacement current. This is not really a current. There is nothing flowing, but it is called as a displacement current. It is caused because of the charge being varying at these 2 points. It is changing the electric field. So this is, we'll say, displacement current, and we call it as ID. Now what we do is that we are going to say, okay, that the Ampere's law, Maxwell actually redefined it. Okay, he redefined the Ampere's law. What did he say? He said that, okay, I'm going to erase this part. He said that instead of, he said this is same. There is no difference in this Ampere's law statement. Okay. However, he said this I, okay, is a combination of I is equal to I conduction current plus I displacement current. He said I is a combination of an addition of conduction current and displacement current. The moment he says that, okay, we can now write this B dot dl as mu naught into IC. Okay, this is IC plus mu naught into ID. What is ID? ID is, you can see, ID is epsilon naught into d phi e by dt. So you can see that this is the new form of Ampere's law. So we call it as Ampere Maxwell equation. This is Ampere Maxwell equation. So that means that he did not originally change the form of the law. Okay, the form is same, but to this I he added a new component called as a displacement current. Okay, which is not really a current, but it's like current. Okay, because it is also dq by dt. Okay, so now he said that the total that B dot dl, if you want to calculate now, that would actually be equal to mu naught IC plus this. Now you want to calculate B at this point using this and using this. You try. When you try using this surface, okay, it actually tells you that you will get the conduction current that is really going through this. And this part, there is no electric field changing in the conductor. So d phi by dt in the conductor inside is 0. So hence the second part is 0. So this part has a value and this part is 0 if you take this surface. Now if you take a surface which is like this, you can see that here this surface that we are taking here, out this surface anyway, there is no current going, there is no electric field also. The only surface remaining is here, and that surface there is no electric charges moving and there is no current. Conduction current is not there. So this part is 0 for that. Whereas this part, the d phi by dt, okay, this part is not 0. That would be actually, there is a certain value, you can compute that. So once you compute that value, you will get the second part is a non-zero. So you get a certain value of B, and it happens to be the same. So in the sense that in here, the conduction current is completely zero, completely present, and displacement current is 0. In here it is, inside this it is, displacement current has a value, whereas conduction current is 0. Okay, so this is basically how he was able to get Ampere's law working in the case of a capacitor. So now with this you can say that suddenly you can see that the magnetic field, okay, is produced by change in electric field even when there is no current. So you see how suddenly symmetry is coming. He wanted to show that, okay, like how magnetic field, like we said that electric field is coming by change in magnetic field. Similarly, magnetic field, can it be generated by change in electric field? You see here, displacement is giving that idea that you can actually, even if there is no current, magnetic field can be generated by change d phi by dt. By change in electric field, you can get the magnetic field. So that is how Maxwell integrated these two views and got a very symmetrical kind of a scenario where change in magnetic field gives electric field, change in electrical field gives magnetic field. To make this happen, he had to introduce a new thing called as a displacement current. Okay, so I hope you understand this. And then we'll move on and to see. So the displacement current at various points, you can see that when you look at uh, how do you calculate the displacement current and all that. So you can, if you try to calculate displacement current somewhere here, so what is the direction of the B here? Okay, look at this. When you are when you are taking B somewhere at let's say somewhere at this point, we want to calculate B, okay, and then you calculate B somewhere at this point. They cannot be drastically different. Okay? That's just vicinity of the points. They must be similar, isn't it? So that means that you know that B at this point is nothing but, when you take it a circle here, the B at this point is actually uh, what we call a tangential one. Okay, so I think the picture that will make it more easier for you to understand is the next picture, B and E vectors. So you see this, that B at the here, the B here is actually kind of if I draw a circle here, it is a tangent to that circle. So B at this point inside also is the same thing, like this. So it's also like that. So you can see that E and B are perpendicular inside. Now in fact, if you actually go and see it from this side, okay, this is a plate, circular plate actually. This is also another circular plate. Let's say you take a view from this side. So take a view from that side. How does it look? Isn't it? So this is sorry, I take a view from this side. Okay, this is the view. I'm seeing from this side. If I see from this side, all these electric fields are going away from us. Okay, the two circular plates here. So let's say this is the plate, end of the plate, one behind the other, and these crosses are all bees that are going away from us, going inside the board. Okay, and then when you see the B, anywhere you draw a circle there, B is actually like tangent to that circle. You can see these are the B direction. And at every point you can see the B and E are perpendicular everywhere. So if you take B dot dl over this circle, you will get inside whatever the magnetic field is there, that flux, electric flux, how much it is changing, the d phi by dt of the flux inside this area, whatever the flux is there. Okay, variation of that flux with respect to time will give you basically B on this through this equation, Ampere Maxwell equation. Okay, so that is the idea. So we will when we work out some problems, I think you will get a better understanding of this. Okay. So what I want to now talk about is uh, the Maxwell's equations, in the sense that Maxwell finally said that finally was able to integrate magnetism and electricity very nicely. Okay, he was able to integrate magnetism and electricity very nicely. But not all of them are his own equations, but he finally integrated them and said that magnetism and electricity can be completely given by 4 equations. Okay, just if you take 4 equations, they are called as Maxwell's equations. Both magnetism and electricity, how they are related, can be explained in just 4 equations. So what are those 4 equations? First equation is called as Gauss law. First one is called Gauss law. And we all know what is Gauss law. Gauss law is nothing but integral of let's write it a little bigger. Integral of E dot dA over the surface or full area will be actually equal to the charge that is enclosed divided by epsilon naught, Q divided by epsilon naught. This is Gauss law. We already know. The Gauss law actually gives you a very nice way of understanding electric field from the charge. Okay, the first level. Second one, we call it as Gauss law for magnetism. This is for Gauss law for electricity. Second one is Gauss law for magnetism. What is Gauss law for magnetism? It says that integral of B dot dA over any closed surface, integral of B dot dA over any closed surface is actually equal to 0. What does that mean? That means actually you take any kind of a closed surface, okay, and over which you compute the B into A, which is called magnetic flux. Okay, if you take that, if you add all that, it will become 0. Now, you know what does it mean? It actually means in the case of charges, the electric field is always connected from a positive charge. Let us say there is a positive charge and there is a negative charge. Electric field always is between positive to negative charge. That means the electric field has the end points. So there are end sources and sinks are there. Okay, electric field starts at positive charge and ends at negative charge. So we would say it has a source here and it has a sink here. Electric field has sources and sinks. Hence, you can actually say that electric field, if you take all the electric field on the closed surface, we will say what is the source of it. We can calculate, which is the charge. In the case of a Gauss law for magnetism, we will know that if you want to do the B, okay, B, how is the magnetic field? Magnetic field is never an open thing. Magnetic field is always a closed field. It's a closed line. So if you have your magnet here, for example, NS, you have magnetic field lines like this. It's a fully closed line, closes inside. Even when you are having solenoid or wherever you take magnetic field is always a closed loop. That means the magnetic field does not have any source or sink. Magnetic fields don't have source or sink. So if you take any magnetic field in a closed area, if you find out inside there are no sources or sinks, because magnetic field are always closed loop. That is what you are saying here. That's all is the statement. Okay, that is the actual meaning of the statement. Now we shall see that Gauss law for magnetism is given as the second one. What is the third? So third one is what we call Faraday's law. That is where Faraday's law links magnetism and electricity. So we know what is Faraday's law. Integral of. So what happens in the Faraday's law? In the Faraday's law, it's the induction. Induction means you basically change the magnetic field and you will get the electric current. Okay, so it is actually, in some sense, you create electric field using magnetic field. So we say electric field is created, E dot dA, around that, using magnetic field, d phi magnetic field by dt. The thing is, it's minus because it opposes the direction. So rate of, still look at how to read this. Rate of change of magnetic field, okay, produces basically electric field. So in any given area, whole electricity, this kind of relationship tells us that the electric field which is basically taken on a closed surface are what we call in a closed loop. So this electric field actually is taken not as a surface, so we discussed it as a dl, okay, E dot dl. This is what we just now saw. If you see what we calculated, when you uh, when you do rate of change of magnetic field, it creates a electric field. Okay, so electric field over the let me just check that whether it is. Yeah. So this is how the third law says that rate of change of magnetic field gives rise to electric field. Okay, and electric field again in a loop we take it. Okay, this is basically called as Faraday's law. So we have not studied Faraday's law in this form earlier. Okay, we just said that d phi by dt is giving rise to E. That's all. Okay. So now this E everywhere you are adding up and showing that. Now the fourth one is just now whatever we said. That is Ampere Maxwell law. Which is integral of B dot dl is equal to, okay, so mu naught into IC, that is conduction current, plus epsilon naught into d phi E by dt. This is displacement current. So this is basically, see, if you take a the further look at these Maxwell's laws. The first two laws are talking independently on electricity and magnetism. Okay. Second two laws are linking magnetism and electricity. And basically, if you look at this law, it shows how electric field can be created using magnetic field, and this shows how magnetic field can be created using electric field. So all these four put together are called Maxwell's equations. They are very, very famous. Maxwell's equations are the most fundamental equations of nature. And even when later people got into calculating Einstein's special theory of relativity and all that, you still have to get back to Maxwell's equations and show that it works in the new scenarios. When you work on quantum physics, you have to go back and show how Maxwell's equations work. So the concept of so-called electrodynamics gets into this Maxwell's equations. So they are the most fundamental equations that we have to work with. Okay, so now these Maxwell's equations are also in different forms. The form that we are talking about is called as the integral form. So they are also in differential forms and all that. So we are not getting into very too much into this Maxwell's equation at this point. If you remember that this is the conceptually for Maxwell's equations, that is sufficient.